Good.
All right, latches and flip-flops. These are going to be the basic components for, I'm going to just say for the sake of argument, fast memory. There are many, many types of memories out there, but definitely latches and flip-flops are the ones that we're going to use a lot in this class and are definitely used a lot on your basic processor. Just keep in mind that when you talk about RAM or even cache or other large memories, they don't use latches and flip-flops, and hopefully after today you'll see why. All right, so we've done sequential circuits. It's very, as you probably have noticed, your machine has state, so that it's not just one circuit, you run it and then you get an answer. You have state because you want to change what the beginning inputs are and then come out with a different answer, aka if you're trying to add something or multiply, or if I'm trying to move to the next slide of this presentation. So far we've talked about what's called combinational circuit. You have inputs, they go through a circuit, and then you have your outputs, and you're done. Now we want to add state. So your inputs are actually both your combinational circuit and your memory state, and then it goes to your output. This is a little more real life of how your computer operates. So keep that in mind. Your inputs not only are coming from maybe your keyboard, but they're also coming from the state that your machine is keeping, or the current contents of memory. Right, so keep in mind that the same inputs can yield different outputs depending on what your memory is. If I push the key while I have one terminal highlighted, it puts the K there. If I go over to Word, I push the K, which is the same input. It's now in maybe Word because the memory or your state has been changed. Everyone see what I'm getting here? Okay. So a memory needs to have three properties. It should be able to hold a value, you should be able to read that value, and you should be able to change the value that's saved. All right. Hopefully that's at least somewhat intuitive. You need to be able to keep it in memory, aka hold on to it for a while, and then be able to tell what it is and then change it if you wish. All right. So we'll start with the simplest case, a 1-bit bistable memory. All right. It holds 0 or 1. We're going to do a lot of 0 and 1s, by the way. It's going to get kind of complicated. You should be able to read the bit that was saved. You should be able to change. Since it's only a single bit, you actually only have two choices. Set the bit to 1, and then we're going to have something called reset or clear, which sets it to 0. All right. So the idea of a bistable memory storage, here you go. This is going to look a little weird. This is called a static memory cell because it's not going to change. Notice up top what's happening. And this is why the circuits are going to start getting very confusing. Is you have your simple circuit, but then the output of that circuit goes directly back to the beginning. Well, you got to hold memory somehow, so you're going to have a feedback of voltage being applied backwards. Okay? Now keep in mind that since these are inverters, there's actually a power going to them, and that's how you can keep the whole circuit powered and not lose your flow of electricity as it's being run. So up here is static because it doesn't change. You have 1 coming in, it's going to constantly spit out 1. Not exactly what we want, but at least it holds 1 the whole time. So the idea is we want to have, at least up here, some idea of being able to change what the voltage going into it is. All right, that's the high-level view. We're going to step back and actually go to what the basic storage is, which is what's called, well, we'll go look at this, an SR latch. So now to make it even more confusing, anyone want to read to me what this is?
Gross.
No, it's happiness, Caitlin.
Sure.
Gross happiness.
Gross happiness, yes, thank you.
Goosebumps.
Goosebumps.
Oh, no. No.
Wow,
That was just gross.
Man, you're being rough today. All right. What is this? R and S, reset and set.
Diagram.
It's a diagram.
Yeah.
What's a diagram have on it?
Ors.
Lines.
Yeah, what is it? Someone read it.
There's 2 ors.
Someone try and figure out what this is.
Not. I don't know what the other input is.
Oh, is it?
Oh, so this is a negated
Or.
so it's a NOR. We didn't do that circuit, sorry, but it's negated OR. What's being fed into the top negated OR?
It's
It's R and
R in the output of the second one.
All right, sure. We'll stick with that. And then what's S being? I mean, what's the second NOR being fed?
That's in the
The-
output of the first one.
Right.
That's annoying.
That sounds weird.
It is weird. This is strange. But this is the SR latch. This is what we use for basic latching. So Q and Q naught, notice I put Q naught at the bottom, Q on top. They're feedback into the circuit. They're not only outputs, they're also inputs. Keep in mind, back of your mind, that these gates are powered. So that's why the flow of electricity can continue. To figure out how Q and Q naught change, we have to look at not only the inputs of S and R, but also the current values of Q and Q naught. So now our truth table is going to be a little weird.
Yeah.
Okay, so what if S is equal to 0 and R is equal to 0? What happens? Well, that plus means OR, by the way. So 0 or Q naught, well, Q current, Q naught current will always be Q current. Oh wait, remember you're nodding it again. Since it's ORing, we don't, and these zeros are here, they basically become irrelevant, and you just take what's next. Right, an OR. Everyone got that?
Sure.
And then you nod it. Okay, Q current and Q naught current. So when SR is 0, 0, then Q next equals Q current. Whatever value Q has, it keeps. So this is how it stores it. Because if Q, which is the output, is 1, then Q next is going to be 1, and Q naught next is going to be 0, which is what we want. Okay. So what if S is 1 and R is 0? Okay. So S is 1, Q naught is 0 regardless of Q, because again, if it's 1 or whatever, we don't care what whatever is, it's going to be 1 or true. When it's going to be 0. So Q naught next is 0. All right? Everyone pay attention because you're going to be doing your SR latch for Verilog, by the way. That's your next lab.
Great.
No problem. Then this is Q naught goes into the top NOR gate with R is 0. So 0 or 0 is 0. Nodding it is 1. So when SR is 1, 0, then Q naught next is 0 and Q next is 1. So this is how you set the latch. You set it to 1. Q next becomes 1 because no matter what Q was, you're going to set it to 1. All right. Everyone see that? Kind of confusing? Everyone confused? Okay, great. So let's keep going.
You're confused and don't understand? Let's go.
Dude, let's just keep going.
Just,
What if S is 0 and R is 1? Well, again, let's look over here. S is 0 and R is 1. Okay, let's look at the top because we know what's going to happen, right? Right. 1's going into an OR, so that means this OR is 1. You're nodding that, which makes that a 0. That 0 is going to be fed back to the bottom OR,
Both zeros.
but S is 0, so this guy
those zeros, they're actually 1.
is actually 1. So Q
Wait.
naught is going to be 1, and Q is going to be 0. That's calling reset or clearing the latch to 0 because that sets it to 0. Everyone see how that happened? That one should be clear. Let's go back and look at the other one again. Remember, this is the opposite. Now we have S is 1, R is 0. So if, let's start at the bottom, S is 1, going into an OR, we don't care what the other thing is because it's going to be true. Nodding that makes Q naught 0, right?
Right.
Okay. Going up here, we know that that is 0 because that's the only thing that can come out of here. 0 or 0 because we know that the reset 0 is going to be a 0. Nodding that will make it 1. So that makes Q 1 and Q naught 0. So these are the two ways to set the latch, either to 1, 0 or 0, 1. Okay? Let's go back.
So, what whatever S is whatever you set the latch to. So right here we set the latch to 1
Right.
by passing it 1 as S.
Well, hold on. When S is 1 and R is 0, you're setting it to 1. When S is 0 and R is 1, you're setting it to 0. And I'm going to go back real quick to 0, 0, and then we're going to go and see what happens with 1, 1, okay? So you're close, but not quite. 0, 0 is where it's a little complicated because since both of them are 0, we have to basically guess what one is and what's the other. So let's pretend Q is 1 because we set it to 1 last time. Let's just pretend for the sake of argument. So if Q is 1, that's what's being fed into S. 1 or 0 is always 1. Negating that makes Q not 0, right? So you'd have 1 up here, Q naught being 0. And let's just make sure this is still okay. Q naught 0 going up here is 0 or 0. That would be 0. Nodding that as 1, which would then power Q to be 1. So if you put S and R to 0 and Q was 1 beforehand, it stays 1. Do y'all see that? All right, let's pretend Q is 0 now. If Q is 0, remember again 0, 0, we'll have 0 or 0 going down here. 0, 0 is 0, nodding that is 1. So then Q naught becomes 1, which is what we want. We want Q to be 0 and Q naught to be 1, so that's good there. Let's just double check the top to make sure it's good. 1 goes up to this OR. 1 or 0 is 1, nodding that goes back to 0, which is Q being 0. So when you set S and R to 0, it holds its old memory value of Q. Everyone following so far?
So it keeps it the same.
Right. So we have a memory. We actually have a memory unit right now, right? We can set it to 1, set it to 0, and we can tell it to hold its value. All right, let's look at what happens when sadness. Well, yeah, here we go. SR latches are memory. 0, 0, no change. 0, 1, reset it. 1, 0, sets it. Okay. The Q represents the data stored, which is called the state. And we just happen to have Q naught coming out, which is pretty handy in case you need to invert something. Okay, great. All right. Now let's see. Notice for inputs SR00, the next value Q could be either 0 or 1, obviously depending on, right. So that's what they want to show right here, is that if there's 0, 0, then whatever Q was is the same thing out here. But no matter what Q was, when you reset it, it goes to 0, and when you set it, it goes to 1. All right. I'm just putting these out in truth tables just to make sure everyone's clear. Anyone confused by this diagram on the bottom right? This hopefully is clear. You good, Clea? We're good? Yeah? That's the... Kind of? Okay. Stephanie? Okay. All right. What about 1, 1? Well,
Sadness.
sadness occurs is the answer. Okay, so if you're trying to set it and reset it, both Q next and Q naught will become 0. Does that make any sense? No.
But you don't
do that.
you don't need to be passing 1 in 1 because you don't want to be setting and resetting it. Is that right?
You don't want to be. That's correct.
But it may happen.
But right. I mean, circuits are like when someone uses a circuit, it's just like a user with a cell phone. They're going to push every little button.
Yeah.
They're going to try everything possible to mess things up. Yeah.
And then it breaks, and then you're like, oh no, put it back, and then it's fine.
And then your hardware fails, and you got to replace everyone's hardware for free. Can't do it with a software update because the hardware doesn't work, and now you're down a lot of money. Okay. Yep.
Shade.
Looking at you, Intel.
What?
I said, looking at you, Intel.
Yeah, Intel.
Shade has been thrown.
All right. So yeah, let's go look at here if we set both. Yeah. So Q next would be reset. Well, plus we don't care. Nodding that would make Q next 0, and then over here S is 1, so we don't care what Q current is. Nodding that would make it 0. So they both would become 0, which is not good.
Just dumb.
That's bad. Another problem happens is what if you set S and R back to 0 afterwards?
Yeah, both was. That's also
Well,
useful.
then they both become on, except for then they feed themselves back, because look at what happens. Notice these two take the same amount of time to saturate. Okay. So 0 or 0 would make a Q be 0. S or 0, because that's what Q was before this saturated, would be 0, and then going back to 1, which would then feed 1 back to these two ORs. But you're feeding 1 back to both these ORs. When you jump to the next, we'll just say a couple of time units, 1 or whatever is 1, nodding that would be 0, and then same thing back here, 1 or whatever would be 1, nodding that would be 0. So literally your memory would flip between 1 and 0 constantly.
And then you'd have malfunctions.
So, moral of the story, never do SR11. Everyone got that? So when you do your lab and you put an SR11 and then weird things happen, you know you did it right. Okay?
Sure.
Okay.
All right. So we already talked about timing. That's great. Notice there's going to be propagation delays. Here's another way to look at it. Our SR latches. There's different ways to draw SR latches. We don't want to try and draw that whole diagram, so we all make them a box. You can do SR on the left, Q and Q naught on the right. That's okay. You can also do SR on the left, Q and Q on the right, and then put a little inversion symbol afterward. That's perfectly fine. This one's not okay. Why is that one not okay?
Because of inverting.
Not Q naught.
Yes.
Yeah.
It just
Yeah, it's
cute.
cute. Yeah, that doesn't make any sense. Don't do that.
Bad.
You will.
Do that.
Fail.
Thanks, Sydney.
Fail the class.
Okay.
Good. Do that.
All right. So if you have the SR latch, you could also have the S naught R naught latch. What is this?
It's silliness.
It's not silliness.
Don't set it down too sad. It's the same thing as the SR latch, but S and R are inverted.
Nice. Yeah. Let's go with the
Whoa.
truth table.
Wow.
Ignore 1-1 for now. 1-0. That's like if you're trying to reset it, right? Because you're nodding the R, so the R should be 1. You're nodding the S, so the S should be 0. So that's resetting it. 0-1 is just setting it, because of course you're inverting it there. Back to 1-1, you're both nodding them, so that's 0-0, aka holding it. And then if you have 0-0 to an SR, that's the same sadness as before,
As well.
where weird things occur.
So don't do that.
Yeah, don't do that. All right. Any questions so far? All right. So we don't want to have the 1-1 thing ever occur, because everyone's going to be sad. So we're going to try and come up with a way to solve the problem. The first thing we do is an SR latch with control input. So notice in here we have our S naught R naught latch, and then we're adding something before it. Basically we have a third wire for control that is fed into another NOR to help us move it on. So that then feeds the inputs to the S naught R naught. Okay, so what's going on here? Well, the idea is that if control is 0, we don't care what S and R are, because if control is 0, what do we got? Why did I write it that way? These are NANDs. That's why I'm so confused. These are NANDs.
Oh, gross.
So if S goes into, C goes in 0 to here, it's a NAND. There we go. Which makes it 0, nodding that makes it 1. So then S naught R naught has to be 1, and you have no change, just like beforehand. All right, great. Notice, I think we skipped over this real quick. Notice that the S naught R naught latch is using NANDs, while the SR latch is using NORs. Okay? It's ends up being the same thing. Wait, someone missed that?
SR latch is using NORs.
Yeah, SR latch uses NORs. That was the thing I just forgot to mention.
Oh.
While the S naught R naught latch
Okay.
uses NANDs. I mean, you could invert the inputs to the NORs, but I'm just saying the NANDs work as well. Okay. So if control is 0, it doesn't matter what S and R are. It's just going to hold no change, right? Yes.
I'm just stretching.
Stretching. All right. And then if control is odd, then it's going to behave just like an SR latch, because you're basically inverting S and R and then going into the S naught R naught latch, which inverts it again and then becomes an SR latch. Okay. Any questions here? Why? Anyone take a guess why we're all of a sudden using NANDs?
You're the
basic
Bless you.
blocks.
Bless you again. Yes.
Through the basic blocks, you want to keep them different.
They are basic blocks.
Circuits.
Turns out every circuit can be written with NANDs. But more importantly, what's the saturation of this circuit now?
It's 2.
2. Because these two happen in parallel, these two happen in parallel. So it's actually fairly fast right now. Okay. Notice that the control input acts like an enable bit. If it's disabled, it's always going to hold its old value. Only when you enable the control bit does stuff happen. Okay. Why are we doing this? Well, we haven't quite gotten around this last problem down here where we have 1, 1, 1, 1 and you can avoid. But that's where the D latch comes in and actually solves this for us. It's based on the S0 R0 latch. The additional gate generates the S0 R0 signals based on input D, aka data, that you want to input to it, and then C is the control. So again, if C is 0, we haven't changed that. If C is 0, then it's going to hold its value. But now if C is 1, then you're going to put into D is going to change the value of S and R. Notice now D is driving both S and R. Beforehand we had 3 inputs, now we only have 2 inputs. And the point of that is that the input up here and the input down here are going to be opposites of each other. So is it ever going to be possible for both this and that to be 1, 1?
No.
No. So that's the point of this D latch, is it gets rid of that problem where you might have 1, 1, because it forces these two to be exactly opposite, and the control line to tell whether to hold it or not. But again, you go ahead and go through it. Oh, excuse me. If D is on, then you're setting it to 1. If D is off, then you're resetting it to 0. And then C is what holds it to no change, and we don't care what D is. Okay. Now, all right, so this is the basic latch. What is, all right. I've said this a lot, but someone else tell me, why is this latch better than the previous ones?
Because there's no bad input.
There's no bad inputs. There's also only 2 inputs, which is great. Hold it and the data value you want to set. Okay. Any questions on the D latch? Nothing yet? Okay, great. Now let's take a break here. Wow, we're going to do K-maps without even talking about them.